Okay, so today we have Jalaj from Rutgers who's going to be telling us about almost exact bounds on factorization norms, which are important for differential private deep learning.
So, hi, everybody. Thanks for coming to my talk. Please, I don't believe I want to cover the entire thing. If you have any question, please free to stop me at any point. This is a joint work with Monica Hensinger, who has now moved to ISTA. She was at University of Vienna before, and Sarvagya Upadhyay, who is a researcher at Fujitsu Research Lab. And part of this work appeared in SODA this year, and there are some new results that I would like to share with all of you as well. So there are two ways I can probably give this talk. One is more from a mathematical perspective, functional analysis perspective, where we look at certain matrices and we are interested in something called factorization norm. And these norm has been studied a lot in mathematics and computer science, and actually mathematical physics as well. So we will look at special class of such matrices, and we'll try to get almost exact bound, and it will become clear what I mean by the word almost as we go on. But probably for the audience here, it's the more important perspective is the privacy perspective. So the norms that we will be looking today in this talk are have a direct application in privacy. So actually, they characterize the mean squared error or absolute additive error for linear queries. So they're important for that. And we will see their application, how they can be used in continual observation as well, as some of your colleagues have already pointed out in some of their paper as well. So what I mean by exact, actually, I would be precise with respect to constant as well. So I'll try to get almost non-asymptotic tight bound over all dimension that we'll cover about. Privacy, of course, we are all differential privacy would be the one we'll care about. And what I mean by continual observation is that we will be outputting at every time epoch. So we'll get some data and we'll output some function at every time epoch. So let me quickly jump to the problem statement. So I said we will be looking at a special class of matrices. So basically, the class of matrices I will be thinking of is defined by a monotonically non-decreasing increasing function. So basically, it's a lower triangular matrix I will look at. And each of the entries of this lower triangular droplets matrix is defined by evaluation of the function for that index. So basically, this is the lower triangular matrix. And as it turns out, this if I multiply with any vector, it gives an output the ith coordinate. It kind of solves the problem of decaying sum, which has been studied by Cohen and Strauss from like 2003, I believe. And I mean, Edit might correct me here if I'm making a mistake with the citation. But in general, if you think of f as being a constant function, this is actually the continual observation problem that people in differential privacy have studied since 2010. So this captures a lot of different questions that you might worry about. And we will be looking at two specific norms, which are both called factorization norms. So yeah, just something which is bothering me. So factorization norm, which is the first one is some people call it gamma 2 norm in computer science, but coming from operator algebra, it's called completely bounded spectral norm. It is just you try to factor the matrix into some two matrices, and you look at the row norm and the column norm of those matrices. So the row norm and the column norm of that matrix, and try to minimize this product. It's not obvious it's a norm, but this objective function, if I think of this as optimization problem, this has a very nice semi-definite characterization. And that allows you to prove that they are norm. Fairly straightforward. You can also prove from the first principle if you want. So this basically in privacy, it characterizes the absolute additive error. So that's why it is interesting from privacy perspective. The second one we'll worry about is what is known as gamma F norm. And this gamma F norm is also studied in functional analysis too. Basically, instead of looking at just the row norm of L, you're looking at the Fourier norm of L. And as it turns out, this actually characterizes the mean squared error. So both of them have natural reason why we should be studying from privacy. They have been studied in other areas of computer science as well, like complexity theory and quantum channel capacity, but we will not be going into those details. So what we will be mostly concerned about in this talk is their application in differential privacy and how we can best get the factorization norm for this class of matrices. So basically, I will kind of make the problem a little bit different. And remember, in the previous one, I did not put any constraint on what my L and R are, but I will put another constraint saying, well, my L and R are also both lower triangular matrix. It's more for application, make it easier application in continual observation, as well as now if I have a lower triangular matrix, and if say they are nice toplets matrix, it allows matrix vector multiplication much simpler. It becomes unlog n because I can decompose it in nice Fourier basis. So this is the kind of problems for the upper bound we'll try to solve. For the lower bound, I don't put this restriction. And of course, this is an upper bound on the previous, actually the factorization norm. So all good for us. Okay. Any questions so far? So if not, so before going there, I mean, factorization, CB norm has been studied a lot. So while working on this problem for a specific set of matrices, we also went about and thinking what else we can say about the factorization norm. So as it turns out, if I'm thinking about now, let's for time being say complex, we can all these results I will say in real matrices because we will worry about real matrices. But because they have application in quantum mechanics as well and statistical physics, where complex numbers are more interesting, like complex space are more interesting. So we'll give some results in terms of like the results about these norms, they will also extend to complex matrices. So basically, if you're thinking about a complex matrix, which is n cross m matrix, the CB norm, the completely bounded spectral norm, is very well studied. Like since pretty much uh, it was given by Schur in like 1911, it has been completely like people have covered it in various form, going from Grothendieck and a lot of people in that era. Hagerup more interestingly. But the gamma F norm has been relatively less studied. So we will be also looking about some properties. What can we say about the gamma F norm? Can we, whatever property we know about CB norm, can we also show similar properties for gamma F norm? And of course, because its application in privacy, we are interested in it. But we believe they will have other applications in functional analysis and mathematics in general. So might also worth looking at just for the sake of math. Just let's get a quick review of what we knew about CB norm and what we want to like maybe show for gamma F norm as well. So for CB norm, this is the definition we have. Just to recap, it's a norm, first thing. As I said, it's a norm. We have a nice semi-definite characterization of this optimization problem. So it's a norm. We can prove using that semi-definite characterization. People also call it factorization norm, as this topic goes. And mostly because one person gave this nice Steinsberg representation into the factorization form. And that's since then Fisher in his book called it factorization norm. And people in functional analysis stick to the factorization norm. People in operator algebra stick to calling it CB norm or quantum mechanics people. And people in matrix theory started calling it Hadamard operator norm. And the reason why they call it, so you will find all these names in the literature. So if you look for any of these, they kind of all are the same. And Matthias called it Hadamard operator norm because of Hagerup's beautiful characterization of CB norm in terms of Hadamard norm product. So that is exactly the dual characterization. And this dual characterization is just a simple thing. Many of these results were rediscovered in computer science in like 2009 paper by Lillian L. I'm forgetting the second author name, but some of them have been rediscovered. But yeah, you can see these in like. Unfortunately, the problem is that this paper is in the manuscript form. Hagerup never published it, so it was only circulated among mathematicians. But these results were known from like 1980s. There are other representations as well that came from people who are interested in quantum mechanics, like especially John Waters had this nice representation from Chow Ziemowski. So there are many ways you can represent this gamma 2 norm or CB norm. So we set about like understanding what are the things on these properties can we also extend it to gamma F norm so that it facilitates our work in privacy as well. Because I mean, for gamma 2 norm, we can use any of these and use it for privacy. So some of the properties that we were able to prove for gamma F norm, first, it is a norm. I've been saying it is a gamma F norm without explicitly showing, but basically we were able to show that this is a norm. Nikolov gave alternate proof for this in a private communication to us, which actually goes from the first principle. So there is a couple of proofs that you can have for this. Unfortunately, it was not written before a paper. The other thing you can say is that gamma F norm has a nice bound with respect to CB norm, both upper and lower bound, and both of them are tight. Very simply, I can pick A to be identity. Sorry. If I pick A to be identity, then I get this bound. And if I pick, say, for example, A to be 1,1 transpose, I get the other side. So it's tight as well. There are matrices that achieve both the bounds, but gamma is generalizing these two space. Now, if I am only concerned with real matrices, which what we would expect with privacy, then optimal factorization consists of real matrices. You do not have to go to complex space. You can go to complex space sometimes because it helps you with update time and compute time, but real matrix factorizations are enough. They achieve the optimal bound. If there is an optimal factorization, it can be achieved by real matrices. So in particular, you can solve the semi-definite program that we'll talk about only on the space of real matrices. Some other thing that we prove for any complex matrices is that it can be casted as a semi-definite program. I've been saying this, and I will show this very explicitly in a couple of slides. And with semi-definite program, it's always a problem whether the primal and dual will match. As it turns out, Slater point exists, so they do match. So that allows us a nice lower and upper bound proof. More importantly, I never explicitly said that my factorization L and R are finite dimensional matrices. They might just lie in infinite dimensional Hilbert space, for all I care. But we can actually show that optimal factorization can be achieved by finite dimensional matrix, and this is important for any real-world application. People in operator algebra do not care about finite dimensional matrices. That's so as such, but it is important for people us. And the last thing that we were able to show was you can relate gamma F norm also in terms of two norm that is more common for matrices, that is the Frobenius norm and the Schatten-1 norm. One part of it was we discovered later again by Nikolov. He told us that this was proven independently using a completely different bound. but there's a much simpler bound, I think. In our opinion, it's a much simpler bound that we have. Okay. So these are some of the properties we were able to prove. We also have some other characterizations of gamma F norm, which will not go into detail. But you can have different semi-definite programs, all of which are equivalent, but some of them are more amenable for certain analysis. And we are working on a much updated draft of this paper, so all of those details will come in this paper. Okay. So as you're saying, so all our result, like the lower bound, upper bound, kind of relies on this semi-definite characterization. So what is the semi-definite characterization I can give of gamma F norm? Well, if my matrix is a real matrix, I am considering only with real matrices, all the things extend to complex matrices, except that you change things from symmetric to Hermitian. That's about it. So the primal form I get is I can write is a semi-definite program where I have a PSG matrix P such that the first I columns, all the diagonal entries are bounded by some values, the objective value that I want to achieve, C, and the rest of them sums up to C. A little different from CB norm characterization. In the CB norm characterization, you do not have this constraint. The only constraint you have is, so I should write, so you do not have this constraint. You only have a constraint that here it is 2. So 2 times n. If I am looking at CB norm, the rest of the constraints are the same. So in particular, P has the same entries as the matrix A. J, by the way, stands for all one matrices. So J is all one matrix. So these rest of them, whoever knows about CB norm, they will recognize them to be the same. Now, using similar Lagrangian duality and change of variable, we arrive at a dual problem where the objective function goes something in the form of quadratic form. And here this bullet is again Hadamard norm. So Hadamard norm is just, I took two matrices and entry-wise multiplication. And the other constraint, the different constraint from CB norm is that, CB norm is that I have a restrictive constraint of this form, that my W1, the first n entries, are all same. And this comes because of my constraint here. I should see this constraint coming into play because of the difference in the sum of the diagonal entries are bounded by C. I mean, you can write it as bounded by C as well without any problem. Okay, so this is the dual characterization that we wrote. I mean, there is another simpler dual characterization that might be more amenable for proving other lower bounds, but you can use this dual characterization to get nice lower bound. And that's what we will show in the next few slides. Okay. So how do I get about, so I can simply explain how we came about the primal problem. And that is very simple explanation. So I can write this, first of all, I can scale my matrix L and R by some constants to make sure that the Frobenius norm of L and the column norm of R is same. That goes without any problem. Sorry, row norm of R is same. Column norm of R is same. So I can make that assumption, and then I can write any factorization of L and A. Is simpler this similar problem. I take a PSG matrix such that X2 is just my matrix A LR, and X1 and X3 have the property that X1 is just a Frobenius norm of L, and X3 is just the column norm of columns of R. So that is basically what I do, and that's where you get that the sum of the diagonals here, diagonals is upper bounded by C, and you get the columns of R is upper bounded by C. Combined by that, I made this simplifying assumption that L, the Frobenius norm of L and column norm of R are equal. So you actually have to just worry about one of these two. So this pretty much gives me the Primal form. And the dual is just standard, like doing the calculation using the Lagrangian, the standard thing you do for dual, writing a dual. So nothing very insightful there. Okay. So what can we do with this? Well, let's look at the most simplest example of my matrix M, which is defined by function, constant function, all one function. So I am, as I said, I am interested for upper bound. I'm interested in finding factorization, which are lower triangular, such that Frobenius norm of L and column norm of R, their multiplication is bounded. They have application in private online of convex optimization. Google has put out a production for this. In some sense, the only production level deployment I know of private learning. So how do we get about it? Well, I will give one slide simple proof of the simple bound, and then I will get to the much tighter bound, let's say. So basically, I use just trigonometry now to compute LNR. You can, and now with a much better understanding, there is another simpler proof for this, like how you can achieve to this LLR matrix. But basically, I construct a lower diagonal toplets matrix. Now, both L and R are lower diagonal toplets, so multiplication is much faster. My LKth entry looks a little bit funky, but it is in a nice higher power of cosine function. That's why I said it has a nice trigonometrical inequality to work with. Now, this I can compute very easily, actually. So the column norm of R is just I will take just the first row, and that's first column, and that's compute its norm. Now, we had a different proof using real analysis, but Rajat Bhatia told me when I was giving this talk last year once that this is something called Wallace inequality that people have studied in for some time. And this Wallace inequality basically gives me a bound on Li squared, 1 by pi. And it is actually also a very nice tight lower bound as well on this. So once you have this, you can simply see this is log n by pi. So you get log n by pi. So this is one simple one-line proof. And now you can compute the Frobenius norm of L as well, because all of the entries are same for L and R. So I have done all the hard work here, quote unquote. And then I get the upper bound by just computing the Frobenius norm, which comes like n times 1 plus log n 4 by 4. There is 4n by 5 because I have not explicitly stated what are the, like when I do the harmonic sum, some terms come differently. So I did not explicitly compute. So for everyone, it's just you can think of it ln by pi. So this is one slide proof for the upper bound. The upper bound, that is what is in the soda paper. For the lower bound, I will use this dual factorization. So let's go with a simpler lower bound proof, which is much simple to write. So I will define, this should be Z. Q. This Q matrix looks very funky. There is a reason to pick this matrix because if you think of all the entries, they are again forming a harmonic sum. So that's the reason we picked it. There's a reason to pick the negative on the other side. Sorry, should be 1 by 2. So negative. I have been Incorrect, sorry. So this is 1. My bad. The reason to pick this matrix is that it is a principal submatrix of a nice droplets operator. And this droplets operator have a very beautiful property that its associated symbol has a very nice Fourier expansion. And once you have this, we can just pull out deep result from our droplets algebra, basically saying that what would be its spectral norm. And basically the spectral norm of a droplets matrix is just the supremum of its symbol. That's about it. So supremum of this is pi, easy to compute. Theta is over the unit ball, and then I get a nice lower bound. If I do this computation, I get this nice lower bound. So this is in some sense a simpler proof, but we can get a much tighter proof. This is still like gives me an order 1 difference. Sorry. And I promised you that I will also care about constant. So there is a 1 that is missing here, which matters when you're looking at optimization because your dimension will come into play. Your D and D can be of order 1 billion, so that can come in play, and that would make things harder. So I really care about this 1. So I'm fighting for this. So how do I get about it? Well, stronger bound. Now just take the nice characterization I have in terms of dual form. So I will use from the dual form, I will get this inequality, or you can use the result that is known from like 2015. And for upper bound, I will pull down the lower bound by half, and I will pull down the upper bound also by half. So kind of converge them in the middle. So for the upper bound, I will use what we showed, that gamma f norm is upper bounded by square root of n of the CB norm. And then I will use another characterization of CB norm that is known by Hagarup manuscript. And the final property I would use is gamma norm. Gamma f norm is also a norm. Okay. So you recall the semi-definite characterization. What did we had there? I had this nice dual form. So all I have to do is I have to find a candidate z hat and w that is in the constraint space. That's all I have to do. So I pick them. And I pick them in this nice way. I mean, of course, they have to satisfy all the properties. So I pick them in this nice way. So suppose your matrix A is U sigma V transpose. I don't know what U and V transpose is for now. I'll pick this to be Z. This is a lower bound proof, so there exists a matrix. I know that. And my W is, as I have to ensure that W1, the first entries has to be same. I pick 1 by square root of n. And W2, because the norm has to be same, I just also pick them 1 by square root of n. Both of them are satisfied. Now, if I look at it, the nice thing is that this Hadamard norm and everything with W transpose kind of combine back together very nicely. And I have one line simple linear algebra that I can use to prove that gamma f norm is lower bounded by 1 by square root of Schatten 1 norm. So this is a much simpler proof than the proof that existed before. And I mean, I am biased, but I think I like this proof more. But basically, once you have this proof, all you have to worry about is compute the Schatten 1 norm of A. And Schatten 1 norm of A is just the sum of singular values. And as it turns out, the sum of singular values is very well studied. So I will now use that my matrix M is n cross n matrix. It's a lower triangular matrix. So that previous result was for any matrix. I'm now looking at my specific case of this lower triangular matrices. So there is a paper by Gilbert Strang which computes the ith singular values of M explicitly. And it is in the form that the ith singular value of matrix M where M is lower triangular all-one matrix, is just cosecant function, some cosecant function of 2i minus 1 by pi. And I can just use the property that cosecant of x is greater than 1 by x, again, basic trigonometry, to get this lower bound and then just integrate it over all i's. And basically doing that integration, we get the lower bound. So now I have a lower bound, which is like 2 by pi. And 2 by pi is plus something more. So this something more kind of comes into play, not exactly half plus something more. So this, and in the end, kind of comes to be something like 0.52 or something. I did some calculation like long time ago for n going as far as 2 to the power of 50. So, and then this extra term is there. So it's not that much. Now, what about the upper bound? So this is something that is not in the soda paper. So how we can get to the upper bound? So I will actually go back, take a step back and say, oh, well, I know this is a norm. So I break it down into two matrices, which are easy to understand. So one function is just all one matrix, very easy. And the other one is matrix C, which is all ones in the lower triangular and minus one on the upper triangle. And the diagonal is one. So good. Now, if I look at this matrix 1 transpose 1, its CB norm or any factorization norm is easy to compute because I know the factorization simply. So it's easy to compute. That is square root of t. What about this matrix C? Now it looks okay, but it's a normal matrix. That's one of the reasons to look at it. And I can explicitly compute the singular value again, and they are just power of roots of unity. So its singular values are negative, eigenvalues are complex, but singular values are just power of roots of unity. So I can compute the norm. And when I look at this, the other thing I can show is that C transpose C, every diagonal of C transpose C, the diagonal entries of C transpose C is a constant. It's the same value. Sorry, I should not say constant. It's the same value. So basically, trace of C I can compute, and from there I can compute square root of C transpose C. And now I can use the characterization from Hagarup to actually prove that the CB norm of C is just 2 by pi log t. Log t comes by using this summing all these powers and the absolute values of it. And you can do the De Morvis theorem and get to log t. So basically now, in all total, I have gamma f is square root of t half plus log t by pi. Now, we ran computed these values numerically, and the difference now is down to of order like 0.02 between the upper and the lower bound for n to be of order 2 to the power of 50. So that's why I said it's almost exact. It's not exact. So some new result that I also wanted to present today, like this is something that just pretty fresh. We can extend these things to any monotonically non-increasing functions. So again, we will only restrict ourselves to looking at lower triangular factorization for our ease of calculation in some sense, and also because it makes things easier in the streaming setting. So this is the problem we started with like about a year and a half ago. We solved the case for constant function last year, and what we can do if I have function which is just a monotonically non-increasing function. And this is also important because in privacy, because you usually assume that older data loses their significance. I mean, Cohen and Strauss in their paper has this very nice motivation why I should care about some decay function, like which are polynomially decaying or exponentially decaying. Actually, polynomial decay is much tricky to motivate, and they motivate that in the paper. And in particular, I can also think about the threshold type function, which covers the sliding window problem, that I have up till some window W, I have 1, and then everything else is 0. So this is also monotonically non-increasing function. I can look at it. So what can we say? Well, for this general result, now this has application in other areas other than privacy, so that's why I have this general result. If I have a monotonically non-increasing function, I can compute the gamma 2 norm of CB norm, by some function AI, which I will make explicitly, and just using the factor that gamma F norm is square root of n of gamma 2 or CB norm, I get this inequality. Now, what is this AI? That is the thing. Now, AI depends on the function itself. And it depend on in the form of evaluation of Bell's polynomial. Now, Bell polynomial comes a lot in innovative combinatorics, probability theory, and a lot of places, pretty much, since Bell discovered it in 1920s, I believe. But this is nice Bell's polynomial, or I can write it as, if I don't want to worry about this function, I can write it as what is known as an ODM polynomial. But Adomian polynomial is not that different from Bell polynomial in some sense. They are siblings. So I will write everything in form of Bell's polynomial because it's nice to study. Now it looks like, oh, what do I do with this weird function? Now I reduce the problem of computing this to another function. The nice thing about Bell's polynomial is that it has a nice recurrence relation. So I can actually compute it using simple dynamic program. And if you use Compton's book, Comptet actually have that recurrence relation, and you can use whichever language you want and write a dynamic program, which would probably be half a page, like not even 50 lines of code. Now I can explicitly compute all these values for any function that you care about, really, literally. Any monotonically non-increasing function, which maps from positive natural numbers to positive real numbers. So I have explicitly taken out 0 from it. So this is good, and the proof is also, like, again, very simple. It's something that you can explain it to someone who just took the second year calculus course. So the proof is, again, page long. Previous proof was much more complicated. We found this simple proof, so I like this proof now. So what I would do is, I have this function f. I will construct another function which has this variable x, infinite function, infinite degree function. And now what I am concerned is, I will look at what would be the polynomial if I take the square root of this function. Now, why I'm doing that? Well, if I look at the matrix multiplication, and if I look at two diagonal matrices, and I put the entries G1, G2, G1 here, all these values, squaring this function G is same as taking this row and multiplying with that corresponding column, and you get to FIs. So I have reduced the problem of finding the factorization on matrices to finding a square root of a polynomial. So that's why I care about this. Now, as long as I have a polynomial which has a formal power series, I will have a square root which also has a formal power series. So this is without any loss of generality again. In particular, for any Toeplitz matrix, lower triangular Toeplitz matrix, I can write this thing. So that's good. Now, how to do about it? So now the basic observation we look at it is that if I take kth derivative of my function g of x and evaluate it at 0, all the powers cancels out, and I get the kth coordinate. Sorry, kth coefficient. So that is what we are going to do. I know on left hand side I have this simple function, so I want to compute all the coefficients of my polynomial G. So from one way of doing this, I get this. Now there is another result from like 1800 from Urbagast and known as Fadi-Bruno formula, because Fadi-Bruno also discovered it independently in 1885. So as it goes, the person who discovered things at last is the person who is known, often given credit. But basically, Fadi-Bruno or Vargas, the Fadi-Bruno formula, gives me a nice way of computing this differentiation. And it was not until, so Fadi-Bruno's formula has more complicated look, but it was not until 1940s or 50s people saw the connection, like combinatorics people saw connection with Bell polynomial, because whatever was summation inside, it actually was enumerating a partition, which is characterized by Bell's polynomial and from his Bell's original thesis. So basically, you do these two things. You look at these two formulas and equating the two, as we do always do in mathematics, to combinatorics. Do something in one way, in one side, or the other way, the other side, and equate them. You're doing the same thing for same function. Equating to two sides, you get the result. So that is basically the proof of that expression that looked fairly complicated. However, for our case, I would like to have simpler expression if possible. So we showed that for a special class of function, which are of interest to many of us. Basically, if you have looking at polynomial decay function or constant function or exponentially decaying function, what can we say? So if f of x, square root of f of x has only positive coefficients, then I can write things much easier. Then I can write the gamma 2 norm as just a squaring the function evaluation by 4 and summing them all together. And same thing with gamma f norm. Now it comes from just the property of gamma f. And that gives me a nice bound on both gamma 2f norm and gamma f norm. And I can use the characterization in privacy to get my privacy result. So why I care about it? Well, if my function is polynomial decaying, this function f of x is what is known as Jean-Carré function. And this has relation, I mean, it's also called polylogarithmic or digamma function. And we know from like long time ago that its square root has only positive coefficients. It comes naturally in mathematical physics as well. The other function that we can think about is exponential functions. And for that also, we know that if I take the square root, they will only have a positive coefficient. So you just compute all these function evaluation and you get either the generalized harmonic functions or you get this looking function. You can also upper bound it by a simpler function. That is just a calculation that goes to grade 11. So that is pretty much what you can do with any general function. For special class of function, you can do it. There is one class of function we could not do much about it, is polyexponential function that has been studied in Cohen-Strauss as well. We could not do it because we do not know if it has this nice property that its square root has a positive coefficient. My conjecture is that it has, but I don't know. So polyexponential still remains open. Now, we can just directly plug all of this to get nice results in privacy. Gamma f norm and gamma 2 norm characterizes my counting in mean squared as well as absolute error. So I can get the same bound. I don't know how much time do I have.
Another 10 minutes.
Okay, so I will probably not go through some of the details. So differential privacy, I hope everybody knows. I will not go into details. But basically, we use what is known as matrix mechanism which was studied by Lee et al. In 2010 and has been renamed as, also people call it factorization mechanism, and has a lot of application. So there is a paper where I copied this from a paper, I think HDMM paper. I copied this text from there because they have probably the best uh, survey of all the things that has been done, like in way you can use matrix mechanism. So you use this basically to say, well, if I have A and A is equal to L times R, then I can run this simple algorithm. I can compute Rx plus Z, where Z is just the variance of Z is just the column norm of R, and then multiplying with L is post processing, so preserve privacy. And then you get mean squared error, which just gives like the Frobenius norm of L times column norm of R times your scaling parameter. So this is known from like Lee et al. From 2010, and that's basically what we use. We also can use our lower bound to prove nice result for parity query actually. So for parity, things are very simple. My matrix A is just some matrix of 2D 2 to the power of D Hadamard matrix, dimension Hadamard matrix. Basically, this was my dual characterization. I know from that dual characterization that the gamma F norm is lower bounded by the Shatton norm of A by square root of M. In our case, square root of M is just D choose S. I know that all the similar values of my A is 2 to the power of D. So I just sum them up. And plugging all of it, I get as a result, gamma F norm is D choose S, which I believe is optimal to the constant. So this is how you can prove for S parity query. You can we have beliefs that it can extend to something like marginal queries as well using this characterization. But that's something that we are working on at the moment. Again, for counting, you can do the same thing. Basically, we wanted to get rid of this big O notation and get concrete bound. So we figured out that like, and also pointed in the paper by Denisov et al. That binary tree mechanism, which is a very standard mechanism people have used, basically it does like construct a binary tree, and when you want to compute the sum, you take the diadecal double for that sum and add each node, you add noise, which is scaled by some Gaussian uh, samples. Just add that. You get an error which goes like log square t by log 1 by delta. The thing that was pointed in Denisov et al. Was that binary mechanism has this nice, very bad thing about erratic noise addition. So it's complete. It does not like when you're using in practice, it's a problem. Because I mean, at this point, you have error which is log t, and at the very next time, you have error which is constant. After does not depend on t at all. So that's the problem in practice. So for using our bound on gamma F norm for counting matrix, you basically get the optimal bound. Because the lower bound, because if there's an equality here, you have a lower bound and upper bound, and both since the factor here of gamma F is off by like 0.02, it actually goes off by very small number. And we can also use that because we have just done all the hard work of writing the SGP form. You can actually prove that binary mechanism is suboptimal. You can provably prove that. Because binary mechanism, I can think of binary mechanism also as a factorization mechanism, where my factor has some nice special form. And if I calculate the Frobenius norm of the left factor and column norm of R right factor, I can evaluate this to be exactly this value. So it's simple doing counting. And as we have shown, this is suboptimal when you concern with constants. So binary mechanism is provably suboptimal with respect to constant. So just wrapping things up, our current understanding goes, well, combining all these results, most GP algorithm work think about either L2 norm error, mean squared error, or L infinity error, absolute error. The paper by Denisov et al. Gives me uniqueness result for L2 norm. It also gives me some nice results that allows me to think about just the value of factorization norm, and so get the tight bound that we have now. Explicit factorization is known for L2 and L infinity error, which is both lower triangular toplets matrix. So matrix vector multiplication is much faster. Matrix multiplication is also faster. This has been known. Both factorization are lower triangular, as I said. The thing is that we have some results for getting LP errors as well, because we really wanted to understand where does the thing changes from L2 error to L infinity error. So we are trying to use some continuity of norm and understanding how things behave when we look at LP error. There is a recent paper by Nikolov et Tang which talks about LP error, but their error metrics does not directly correlate to us because their error metric goes like expectation of the error, p norm squared and 1 by 2. Ideally, I would like something like p and 1 by p. So we are trying to really understand what happens when I look at LP errors that way. So this is something that we are trying to characterize it. We have some results on this line, but it's not something that that is ready to be spoken about publicly. So this is something I can just jump through because I don't know why. Sorry, I have this slide. This is slide. There are a few open questions. Sorry, so I think I have a question. No, so this is additive error. The difference between the gamma 2 norm, gamma f norm is actually the additive error. It's the additive gap between the lower bound and upper bound. I might have made a mistake. Square is 0.02 log of n, I think. Sorry, that was my bad. So it is 0.02 like log of n, where n is the length. So it goes like, I think, I mean, if n is 50, it is still like above order 1 or something like that. Very small. I can give the exact number. All right. Maybe I have it somewhere. So open question, of course, the first one is sliding window model. I got everything from n plus to r plus, so everything was positive. I can use some nice algebra to get with sliding window. Basically, I can just compute, like construct block matrices, and that if I want to compute error for the last W window, if the W window intersects two boundaries, I can compute the value until here using my algorithm and value up till here into the up till here through our algorithm and compute the difference. The problem that happens is that in my L infinity error, I get a term of log p because of union bound. So that's not completely good. So we are trying to understand what we can do with sliding window. It's an open question, I guess. Our update time and space requirement is kind of not that good. It is amortized log n. And by binary mechanism gives me worst case log n update and update time. And it is, if I am bold enough to say, it matters in practice, because I mean, if you're thinking high dimensional private learning problem, your D is really large. And if you have to do it for every coordinate, it kind of adds up. So it does, I think, matter to get the update time. So can we get the update time, even the worst case, to be log n, while ensuring that my error still goes smoothly, more or less, and has non-asymptotically less error. There is some work on this line by some of my colleagues, which I'm not sure if I'm privy enough to say. but there are some results on this to improve the update time. But still, the error does not get down as low as what we have. We're looking at other applications of factorization norms in these norms. There is some application in quantum computations, like we really would like to get a lower bound on marginal queries. It will probably simplify the lower bound tools we know of so far. Not have much success so far. Like we have some results, but not to the constant, I believe. And as I said, I really would like to understand what is the application of this gamma norm in other areas of computer science as well. So I think, yeah. So with this, I think I'll just stop. And thanks for everyone for your attention. And if you have any questions.